Can announce myself. I'm just kidding. Okay, I can announce that. Yeah. Pull this off.
Samantha Allen, relationships between.
All right, so thank you for having me. Thank you all for coming to UGA so that I can see all of your faces in person, and all of you for joining on Zoom, no matter where it is. I am going to tell you today about a not invariant called the untwisting number that I think is really interesting, and I'll try to convince you it's interesting too. Before I start, I should say two things. First of all, everything that I'm about to say is kind of joint work in progress with Kenan Ince, Seungwon Kim, Ruppik, and Hannah Turner. And when I say work in progress, I mean we've written down all the proofs and we're editing the paper, but 5 people, 4 time zones, it's moving a little slowly. So eventually there will be a paper, but not quite yet. And the second thing I should tell you is that if you are familiar with my work, you know that I don't do a ton of stuff about quantum invariants, and that remains pretty true. But the story I'm going to tell you, the main result I'm going to tell you has a story that is more or less inspired by work on the Jones-Conway polynomial. Okay, so it'll definitely be in there, but you might have to hold out till about halfway through the talk to really see it. All right, so maybe I should start by telling you what I mean about untwisting number, and then I'll try to tell you why you should care. So the untwisting number, just like the unknotting number, is defined in terms of an unknotting operation. So our favorite unknotting operation is maybe the crossing change. And a crossing change, that's a knotting operation. I can, for any knot, do some number of crossing changes and arrive at the unknot, and that minimum number is called the unknotting number. So if I have an unknotting operation, I can get a knot invariant typically. And the one that the unknotting operation that I'm interested in today is called a null-homologous twist. So a null-homologous twist is defined in the following way. So I'm going to take a bunch of strands of my knot. Maybe I will grab those strands like this. And I'm going to take those strands where I grabbed them and put in a full twist to the left or a full twist to the right. So you can kind of think of this as a tingle replacement, or if you prefer. So I'm going to write, say, plus or minus 1 to indicate a full right-handed or left-handed full twist. And for those of you in the know, this is of course not a null-homologous twist because I haven't actually required anything to be null-homologous. This operation on its own is actually pretty interesting, but it's not analogous to a crossing change. because Oyama proved in the 90s that if this is the move you care about, for any knot, it takes at most 2 of these moves. Okay, so that's an interesting topic of its own. I'm not going to talk about that today. What I want is something more analogous to a crossing change, something that is sort of like an unknotting number. Okay. And in order to do that, what I'm going to do is require that this little unknot, let's call it U, that I drew here, is null homologous in the complement of my knot. Okay, and you don't really need to know what that means. All you really need to know, so here's my knot K, here's my knot K prime. All you need to know is that the requirement is that if I give you, whoops, if I look at the disk bounded by this unknot, and I look at the intersection between my knot and that disk, let's call the disk D, then I need the intersection between the knot and the disk to be an even number of points. So let's say 2K points. And I need the linking number of my knot with that unknot to be 0. And the way that I make that second thing happen is, well, that just means that half of these strands should be heading down into that disk and the other half should be heading kind of up out of it. And that, of course, doesn't depend on the orientation of the knot. And now it turns out that this operation is still an unknotting operation. You can get to the unknot via operations like this for any given knot. But it also turns out that it can be arbitrarily large. Okay, so it is more analogous to the unknotting number. And in fact, depending on who you're reading, a null homologous twist might be called a generalized crossing change. And in fact, a crossing change can be realized by one of these moves. Just put a full twist in the right, full twist on 2 strands in the right way, and it'll change the crossing. Okay. So this is the null homologous twist. And now I can define the untwisting number. I'm going to write as TU of K. I think that comes from earlier iterations of this invariant being called the twist unknotting number, so TU. And this is the minimum number of null homologous twists required to unknot your knot. Overall diagrams and so forth. So lots of work has been done with this invariant. There's work of Kenan Ince, who uses various classical invariants and Taylor floor theoretic invariants to put obstructions on untwisting number 1 and various things like that. There's work of Chuck Livingston showing that this is bounded above by twice the genus of the knot. Okay. And there's recent work of Kuchikova, Miller, Ray, and Zakali obstructing knots from being H-slice and connected sums of CP2s. And if you think about the untwisting number and restrict yourself to only positive full twists or only negative full twists, you can get interesting relations in the same way. Okay. So this is I think interesting on its own. So maybe that's the first reason you should be interested in this is it's just a cool unknotting operation. Okay, but really, question?
Obviously not additive.
So the question is it obviously not additive under connect sum? The answer is no, it's not obvious. And to my knowledge, it's unknown. Yeah, it's unknown whether it's additive under connect sum. Other questions? So why might we care about this? So let's say motivation. So I'm going to write down something that's well known to, I guess, knot theorists. So something that knot theorists are interested in is something called the topological, the smooth for genus of the knot. So this is the minimum genus of a surface in S in the four ball whose boundary is your knot. And it's well known that this is a lower bound on the unknotting number, or maybe I should say the unknotting number is an upper bound on it. And a lower bound on this is given by Rasmussen's s-invariant over 2. And in fact, all three of these are equal for torus knots. So the fact that these two are equal, that's Milner's conjecture, of course, proven by Frenholm and Rothka. But in fact, after this invariant, the Rasmussen's s-invariant was defined, you can actually reprove this result just using Rasmussen's s-invariant, and that's a really nice result. And so if I try to replace that G4 with the topological version, so let's say topological analog, I'm going to replace that with the topological for genus, and so now I don't require my surface to be smooth, I require it to be topologically locally flat. Then the kind of analogous lower bound, I'm going to write sigma hat of k over 2. This is just the maximum of the Levine-Tristram signature function, such as like a classical concordance invariant of knots, away from roots of the Alexander polynomial. So this gives a pretty nice lower bound when it works. And more recently, it was shown by Duncan McCoy that the untwisting number is an upper bound. So here's our kind of analogous statement. We should give credit to Duncan McCoy here. And this is a really interesting inequality, and we kind of like a really hopeful conjecture might be that all three of these are equal for all torus knots. Very, very hopeful. I have no idea how to prove that. Okay. But Bader, Banfield, and Lark in I guess 2021, I think, actually showed that all of these are equal for the topological for genus of the 3 in torus knots. So Bader, Banfield, and Lark. We're able to compute the topological for genus of 3 in torus knots using this inequality. Okay, so in fact, it's equal to this. So this I think is really interesting. It's an interesting way of trying to compute a topological for genus. And we kind of hope that we can do this for other torus knots as well. Bader, Banfield, and Lark gave some other families of torus knots where they can get the two bounds really close together, but maybe not quite equal. And so, of course, the idea is to use the untwisting number to compute the topological for genus, but the problem is that even though the topological for genus is difficult to compute, so is the untwisting number, right? Just like the unknotting number can be very difficult to compute, so can the untwisting number. Okay, so maybe maybe we should think about how best to compute the untwisting number. So the way I'm a knot theorist, I deal a lot with knot invariants, and so the way that I like to deal with it is I try to find another invariant that maybe lives between the two, and so that's what we're going to do. Okay. And so I'm going to add. You already have this. I'm going to add another invariant to kind of our running list of invariants. There will be a lot today. And this one is called the surgery description number. So the surgery description number, I'm going to write as SD of K. And its definition looks almost identical. It's the minimum number of null-homologous twists required to convert K to the unknot. And I just need to add like 2 characters to this definition. I'm going to put in front of this word twists, M. Minimum number of null-homologous M twists required to convert K to the unknot. So it's almost an identical definition. What I mean by M twist here, is that I get to do M full twists in a single twisting region. So this is really counting twisting regions rather than individual twists. So it's much looser than the untwisting number, right? If I can untwist my knot by just twisting a bunch in one place, okay, then my surgery description number is 1 and my untwisting number is however many full twists I had to do there. Okay, so this is different. I guess it should be clear from the definition that this is a lower bound on the untwisting number. And it's a fact that I am going to prove eventually today, hopefully, that the topological for genus is also a lower bound on the surgery description number. Okay, so the surgery description number gives me more freedom, but it is still an upper bound on the topological for genus. This, of course, will only be useful if the surgery description number and the untwisting number are ever different. If they're the same, then okay, it's silly. And so maybe that's the first question you should ask me: is there a knot K such that the surgery description number is not equal to the untwisting number? And the answer is yes. But as far as we know, that is a brand new result. So I'm going to attribute that to that long list of people at the beginning and just call it expert. So it's me and my co-authors. So yes, but we only know of 2. Okay, we expect that there are infinitely many. We expect that these 2 can be arbitrarily far apart. But as far as we can tell in the literature and in our own work, we know of 2. Okay, so I'll give you the 2 examples we know of. 1068 has surgery description number 1, but if you are careful, you can untwist it with 2 twists. And the same is true for 11A103. So both of these these values are, most of this are diagrammatic. You could just untwist them. That the untwisting number is not equal to 1. That follows from work of Kenan Ince. Basically, if the untwisting number of your knot is 1, then the 2-fold branch cover bounds a smooth definite manifold with certain second Betty number, and then you can obstruct it. Okay, for these 2 knots. Okay. And that's kind of all we know about the difference between these 2. We don't know if there is an infinite family. Okay, we more or less suspect there are, and we have some in the works that we're working on. We don't know if they can be arbitrarily far apart. We haven't been able to show that. And the difficulty with this is that it's actually pretty difficult to obstruct the untwisting number from being small if you require that the surgery description number is kind of strictly smaller than it. The best lower bounds on the untwisting number are things like a signature function, but the signature function is a lower bound on the topological for genus, and so you're kind of stuck. Yes.
So you said that you expect there to be an infinite family. Do you have any idea like how large this infinite family might be? Like, would you expect this inequality, like them to be unequal, like generically?
The question is, do we expect these two to be unequal generically?
Are there like some kind of
I guess I don't know, because we have such difficulty constructing examples where we can actually compute the untwisting number without using the signature function. It's pretty difficult to, I don't have like any real guess on that. I mean, I would guess, yeah, they're different generically, but I don't really have anything to back that up. The surgery description number for the T3 and torus knots, because we know that this is equal to this, it's going to be exactly the same as them. Yeah. Other questions? Yeah. It's a great question. Is the surgery description number actually easier to compute? Shrug. So maybe no. The list of invariants gets longer. Yeah, that's great. Yeah, so you'd hope surgery description number. It's much looser definition, but it turns out it's hard to compute, and partially it's hard to compute because these lower bounds on untwisting are hard to compute if you don't use the signature function, and that's also going to be a lower bound on surgery description. And maybe I will throw in a theorem here that kind of shows you why it's not actually any easier to compute. I won't say any easier, but much easier to compute. Maybe I'll call these two theorems A and B. The first is that the surgery description number, okay, that's of course less than the untwisting number. And it turns out that's less than or equal to 3 times the surgery description number of the knot. Okay. So even if you found a family where they were arbitrarily far apart, the ratio between the surgery description number and the untwisting number, it's going to be at most 3. And if you look at something called the algebraic versions, which I'll define a little more carefully in a moment, this basically just means I want to get to an Alexander polynomial 1 knot instead of the unknot. That's what algebraic means. It turns out I can do this for the untwisting number and the surgery description number. That first inequality is, again, clear. Those two are even closer, even more closely related. Okay. So it turns out you might hope that you have a lot more freedom, but you kind of don't. Okay.
That's really good question. Another definition. You're just allowing as many twists as you want.
Yeah.
In any of these ranges.
Yeah, that's right. Yeah, so the question is about the definition. Question is about this definition, right? I'm let as many twists as you want in any given twisting region. There can be multiple twisting regions, and the number of strands and the number of twists can be different in each region. Yeah, so lots of freedom. Okay. All right. So this kind of splits the story into 2 pieces, right? One is like these kind of standard definitions of surgery description and untwisting, and the other is the algebraic versions. The algebraic versions are going to be important because this is going to be actually the path that we take to show that the surgery description number actually lives in between these two. But they both are going to take a similar path through a third invariant. So let's add to our list of invariants. Let's add to our list of invariants. Going to add something called the 2K unknotting number. I'm going to denote this as T sub 2K of K. And that's pretty bad notation. I'll tell you why later. So this is going to be the minimum number of n twists, meaning in any twisting region, I can twist as much as I want, on 2 strands required to unknot K? Actually, no. So the question is still null-homologous. I'm going to say no, just because this is a slightly different invariant and it's an interesting one on its own. So let me make a note here that this invariant actually is definitely a lower bound on the unknotting number, because you can still do that twist on two strands to change a crossing. But if you think about it without the null-homologous, it's also an upper bound on this rational unknotting number that Lucas talked about yesterday. Okay, so that's one invariant, and this is kind of in here for kind of reasons that are not clear, but there is a null-homologous version. So I'm just going to put a bar over the T2K. Oh no, sorry. The question is, should I think of this K as the same as the not K, and that, no, that's a number. And the,
Is there a different invariant? Okay.
so the question is there a different invariant for each value of K? And then the answer is no. So I'm gonna let little k vary over any, I guess, positive integer. It doesn't appear in the definition, yeah. So this is in here for more, the notation is more historical than. And if I put a bar over it, it's just forcing it to be null-homologous. So this is the same as T2K, okay, but null-homologous. And from this perspective, I can kind of see it fitting into my inequalities a little bit. It's an upper bound on surgery description because I'm still doing null-homologous twists no matter anywhere I want, but at the cost of only being able to use two strands at a time. Okay, so it's not quite as free as the surgery description. Okay, so in this last little bit, or I guess the last half hour, I started at 9, right? In the last half hour, I want to kind of tell you two stories. Okay, so I'm going to tell you two different stories. I'm going to tell you a geometric story. And I'm going to tell you an algebraic story. So I'm going to tell you a story about using the original definitions of these invariants, and a story about all of these invariants, but only caring about getting to the Alexander polynomial point instead of the okay. So my geometric story is going to be inspired by work on something called the four-move conjecture. So I'll tell you what that is in a moment. Which inspired work of Shatitsky. Okay, on these T2K bar guys. And that then inspired work of Borodzik on just the bar ones, which are of course most closely related to what I'm interested in. And that's actually going to inspire our proof of the geometric version of that theorem. So I think I called that A. So that's the geometric story. Interesting backstory. The algebraic story, like I said, is really going to help us get at this inequality. In fact, what we're going to be able to do is kind of expand this inequality into the following network of things. So we're going to take the topological 4 genus. I'm going to drop the of k. These all have an of k, right? Going to look at something called the algebraic genus, which is a newer invariant. That we're going to be able to show is less than or equal to the algebraic Serger description number. That is going to be less than or equal to the Serger description number, which is less than or equal to the untwisting number. So we're actually going to get a bunch of things in between here. Okay, but that's maybe not all I can say, because we know the Serger description number is less than or equal to this null-homologous 2k number, 2k unknotting number. And so if I take the algebraic version of that, I can throw that in there. And it does turn out that this in particular is less than or equal to the algebraic untwisting number. Okay, and so you can actually squeeze that in there too. So whichever one of these you like the best, they will all squeeze in between here. I think I'm going to go off into the geometric version of this story next, but are there any questions before I do that?
I look at like a knot table, and look at knots for which T4 top is known versus knots for which TU is known. Which one's more?
So the question is, do I look at knot tables and I look at knots where topological 4 genus is known and knots where untwisting number is known, which one's going to have more things in it? I think topological 4 genus will have more things in it. Lower bounds on untwisting are hard. But maybe I might be wrong. Well, there aren't very many knot tables that have untwisting in them. So, so I think that'll hinder you a bit. I think it would be more likely that there's more overlap between unknown topological 4 genus and unknown untwisting number than maybe one might expect a priori. Other questions? All right, so let's tell the geometric story. So maybe I'll start by just telling you a story. So the beginning of this story is actually a paper of Nakanishi where he defines the Serger description number. And he claims that Serger description number can be arbitrarily far apart from the unknotting number. That is a true statement. But his proof goes through a knot which has an interesting untwisting number as well. So if you're looking for places where untwisting and Serger description might be different, you might look here. And he claims that actually the signature of this knot that he's come up with froze, and it turns out it doesn't. And so there's some small error. It turns out the result is true. So if you try to use his knots, his family of knots, to construct places where the Serger description number and the untwisting number are different, you will get very stuck because it won't quite work. And so maybe you dig a little bit deeper. Okay? And so let's dig a little bit deeper into history to try to tell these two apart. So I'm going to tell you something about the 4-move conjecture. So the 4-move conjecture is based on the following. So I take 2 strands of my knot, and a 4-move is something like this. So I'm just going to add 4 half twists. 1, 2, 3, 4. And maybe my earlier notation in terms of the T2K invariant, this might be a T4 move. And the 4-move conjecture, which to my knowledge is still open and is on, I guess, Kirby's problem list, is a conjecture of Nakanishi, although there is a statement that has to do with links due to Kawaguchi. Says that every knot can be converted to the unknot via a finite number of 4 moves. Okay, I guess this move and its inverse, you do twist it in the other way as well. Basically, the conjecture is that this operation is an unknotting operation. And to my knowledge, that is unknown. It's known by work of Dubkowski and work of Dubkowski-Jablon that it holds for knots up to 12 crossings. It's known to hold for 3 braid knots. It's known to hold for knots that are algebraic in the Conway sense, if you know what that means. But the suspected first counterexample for the suspected first counterexample for a long time was the 2-1 table of the trefoil. Okay, so pretty simple, Not Askidas was able to show that that actually can be unknotted using 4 moves, and he proposes the following alternative first counterexample, which is the 2-1 cable of the figure 8. Okay, so this problem is maybe surprisingly difficult, I think. I mean, that's a pretty simple example. We don't know if it can be unknotted via only moves like this. Okay? And if you try to look into this, a lot of the work will be something like, well, I tried this and it didn't work. There are a lot of actual papers like that. There's something like on the failure, there's actually one titled on the failure of something to detect 4 moves or something like that. So there are lots of papers like that. Yeah. Oh yeah, the question is, what is T2K of the 2-1 cable of the figure 8? I don't know it off the top of my head, but T2K would allow me to do lots more twists into maybe. If I change this floor to any number of twists, I do this. I don't know. If the 4 is a 2, I think we're okay, but I haven't thought much about that.
Another question, Sam. So for these 4 moves, are you allowing any combination of orientations on those 2 strands, or are you restricting to both parallel or both anti-parallel?
So for this, so far for this move, there's no orientation.
Okay. So why can't you then attack this thing? Because like this thing appears in the context of like the double band pass moves that you use to show that like an ARF invariant 0 knot is double band pass equivalent to like a connect sum of trefoils. And so is there like if you study this from that perspective, so I guess there would be maybe some theorem that says like you can get between any 2 ARF invariant 0 knots using like 4 moves with oppositely oriented strands. But then that like maybe that's not true exactly on the nose, because then it seems like you could undo like whatever connect sum of trefoils you get after, moving between ARF invariant equal knots using like the parallel oriented version. Like how well explored is that connection?
I'm actually not sure.
Okay.
Yeah.
Yeah. Well, never mind then.
It's a great question, and I mean, if you can solve the 4 move conjecture, I think people will be happy. So go for it. Other questions?
Why the 4 moves? What's the significance?
So the question is, why the 4 move? What's the significance? I think that it's kind of just kind of one more step in like the stain relation situation, instead of just adding, you know, a half twist or something, add a little bit more. And I think it's just the first case where things get kind of wonky. Okay, so I told you I was going to tell you a story. So this is this conjecture came out a long time ago. It's on the Kirby list. And people have tried to attack it in a bunch of different ways. And in particular, Chatitsky attacked it using the Jones-Conway polynomial. So this was about in 1988. And I'm going to use his notation, but it is different from my notation, so warning. Okay. So I'm going to write everything down first. So Jones-Conway polynomial of the T sub 2k bar of L. This is where his notation differs from ours. This should be the result of performing a single move, null-homologous to the bar. AC is equal to -1 to the k, a to the 2k, times the link, the polynomial of the link, where you've done some kind of smoothing here, plus z times u1 exponent in parentheses of 2k of a for the link where you do kind of the other replacement. And should say these, there are formulas for these in the statement, but I'm not going to write down. So I should say, so this is related to the non-invariant, not the non-invariant, the unknotting operation that I'm going to call a 2k move, which is kind of the unoriented version. If I put a bar over it, it's the same as this, but it has orientation. So maybe I should say bar or null-homologous would have the correct orientations for this to be null-homologous. So maybe this. Thank you. Yeah, you do 2k twists instead of 4. So when k is 2, this is a 4 move. If it has orientations like this, it's this null-homologous 4 move. So if you only care about null-homologous twists on 2 strands, then maybe this is super interesting. It turns out that I think this is an interesting result, but it turns out it's not helpful for the 4-move conjecture. It's just like doesn't give you very much information. So that's a little bit of a bummer. But this work inspired work of Ruppik in 2017. So I should say this is 1988. This is 2017. So a long break in between. But it basically says that if the T2K null-homologous unknotting number of k is 1, so I can find one region where I do a lot of full twists, null-homologous full twists on 2 strands and unknots the knot, then k can be turned into an Alexander polynomial 1 knot using at most 3 crossing changes. Really, it's something like if k is odd, you need 2 crossing changes. If k is even, you need 3, but at most 3. Not to get to the unknot, but to get to Alexander polynomial 1. The way that he proves this is he draws a specific surgery diagram. He has this idea, okay, to turn this doing multiple full twists into something having to do with surgery. Okay. He looks at the trace of that surgery and he uses Blanchfield pairings and he's able to get some restriction on an intersection point. Okay, so that's like roughly the proof of this. Okay. But for us, the kind of groundbreaking portion, groundbreaking maybe in quotes, the portion that pushed us forward is exactly what his surgery diagram was. So if I take my 2 strands and I'm going to do plus or minus k full twists, make sure it's null-homologous. He notices, okay, this part was already pretty clear. We've used that, this has been used in other papers, that a version of a Rasmussen twist can turn this into surgery. So that unknot that I drew at the beginning of our definition for the untwisting number, you can think of giving that unknot a plus or minus 1 framing, blow it down, and then you get a full twist on your knot. Okay. If you want lots of full twists in the same place, you get this fractional coefficient. And then fractional coefficients are inconvenient. And so he uses a reverse slam dunk move. This is one of these kind of standard moves from your Frankenship exercises, which basically says I can break this down into a framing 0 knot that kind of loops my knot and a framing plus or minus k. I'm doing a special case of a reverse slam dunk move. You do something like this. And this is a really cool move, and in fact, I think everything that he does in his paper you can kind of extend. It doesn't have to be untwisting, or sorry, 2k untwisting number 1. It can be higher, and you can kind of multiply. You get a similar bound that we're getting. But it turns out that maybe clearly you can do this on as many strands as you want. That 2 strands isn't important in this picture. And so, let me scroll down here. And then this portion, sorry, you won't have time to write down. If you take as many strands as you want, I've done one here with 6 strands. Okay, and I want to do maybe -5 full null-homologous twist there. I can do this Rasmussen twist and think about this as a 1/5 framed unknot that I'm grabbing. Do a reverse slam dunk, and then I can do lots of handle slides and isotopies very, very carefully. And get something like this. Okay. This is with framing -5, but framing minus, I don't know, 11. Instead of having just kind of 2 grabs here, you would have, I guess, 5. Okay. But it would look basically like the exact same picture. And this is really the crux of the proof that my organization got. This is basically the crux of this proof. Because I went from a full twist several full twists in one region to 2 single full twists. Those plus and minus 1s are going to be can affect 1 positive and 1 negative full twist in 2 different regions. Those regions are completely unlinked, and so it all works out just fine. And if you're really worried about the fact that I went through handle slides and slam dunk moves and rocks and twists to get here, you can work it out really careful and realize that as a diagram replacement, but you lose, your pretty kind of grade presentation here at the expense of doing something like this. And I've drawn here with 2 strands, but however many strands you had over here would feed in the other side. Okay. So you're really, really careful. These 2 are actually diagrammatic replacements, but we never, of course, would have gotten here on our own, or just by trying to work out the diagrams, the surgery description is really where it comes out. Okay. So that's the geometric story. I can turn any odd number of full twists into 2 full twists. So if I need to leave a number of full twists in a region, I just pop one off and then do the odd that are left over and then add it back up. So it either takes 2 or it takes 3. Very similar to Ruppik. Any questions here? I'm going to switch to the algebraic story for a little while. All right. The algebraic story is about this inequality here. And so I should probably tell you what those things mean. So I'm going to add to our running list of invariants one more definition. Or maybe it's many definitions, but in one place. So that's right, this is a definition. So given an unknotting operation, say U, then what we call the algebraic U number, and we'll denote that with a subscript of A, is the minimal number of U operations needed to convert K to not the unknot, but an Alexander polynomial 1. So if your unknotting operation is a crossing change, then the algebraic crossing change number is really the algebraic unknotting number. Okay, if you're looking at untwisting, then the algebraic untwisting number, things like that. Okay, and it's a theorem, Kenan Ince in 2016, that for any knot K, the algebraic untwisting number and the algebraic unknotting number are exactly the same. Okay, so you might think, well, okay, the untwisting number, turns out the untwisting number and the unknotting number can be arbitrarily far apart. These 2 clearly cannot be. They're always the same. It's just kind of taking a level of complexity out. But now we have algebraic versions of basically all the invariants that I've defined for you today. You can do an algebraic null-homologous 2K unknotting number, and so on. And like I said, the beauty is that this is going to give us relationships, not just between untwisting and surgery description number and topological forward genus, but kind of all of these things kind of in between. And so maybe I lied to you a little bit. Maybe I'll add one more invariant and then maybe we'll call it a day. So the last invariant that I want to add to our list is called the algebraic genus. So we're going to denote this G alg of K It's slightly different from what I just said our notation would be, but that's because we didn't come up with this. This was defined by Feller and Lark in 2018. And you should think of it as kind of an optimal upper bound on the topological score genus. Okay, so I'm going to write it down and then I'll tell you how to think about it. So it's the minimum of the difference, so g of f prime, such that f is a Seifert surface for k. F prime in F is a subsurface, with a subsurface of F. And the boundary of F prime is some knot K prime, which has Alexander polynomial 1. Okay. So how to think about this? So basically, first things first, Friedman, of course, showed that the knot has Alexander polynomial 1, then it's topologically sliced. Okay, so this is why I care about Alexander polynomial 1 for knots. It's a way to get topologically sliced knots. Okay, so somehow I'm measuring how far away a knot is with this from being Alexander polynomial 1, and then maybe I go a little step further to get to topologically sliced. Okay. And it's a suggestion of Rudolph, an old suggestion that you construct upper bounds on the topological score genus by kind of doing this thing. What you do is you take your subsurface and you kind of surger it out and replace it by a locally flat disk. Okay. So you're not, it bounds some surface, you're not K prime bounds some surface, you're not Alexander polynomial 1, so you can take that surface out, replace it with a topologically locally flat disk. Okay, and in this you can get bounds on the topological score genus. Okay, so this is some measurement of distance from that being super successful, and it is definitely an upper bound on the topological score genus. It's very strange. Okay. Okay, so I'm basically out of time. So maybe I will just say out loud the rest of the story. It's not so long. So the rest of the story is basically, this was defined by Feller and Lark in 2018. Like I said, it's a really interesting invariant. Duncan McCoy came along and wrote down, I guess some of this was in Feller and Lark's paper, and then some of it we found in Duncan McCoy's paper. So some combination of those three gives you lots of different ways to define this. And in particular, you can write this down in terms of null-homologous twists and in some interesting way. And so that's very cool. And so what you can do based on that is say, okay, this null-homologous twisting definition actually relates the algebraic genus to the algebraic surgery description number. And then it's not difficult to get your inequality from there. Okay. So maybe I will more or less stop there. But just so you know, I've only given you the tip of the iceberg here. Here's a diagram of untwisting and lots of invariants that we would like to know about. Untwisting number living kind of right here. A double arrow, I guess, means it's known that the two can be arbitrarily far apart. A single arrow means either it's unknown or we didn't check it, but if it comes in or out of the untwisting number, we did check it. And so maybe I'll leave you with that.
Questions for Sam?
Question maybe? So earlier in your talk, you talked about the difference between untwisting number and surgery description number.
Yeah.
And I think you gave some examples of some knots where the difference was 1. Mm-hmm. Just out of curiosity, as my first thought for an infinite family for this would be the NN generalized twist knots. Yeah, because these things sort of I guess as a human looking at a diagram, everyone will say, oh, this thing clearly has unknotting number n. Of course, you have to prove that, and I don't know if anyone can actually prove that. But then it's sort of immediate from the diagram also that the surgery description number is 1.
Okay.
And so I'm sort of curious, has that family been studied? Have people seriously tried to like get lower bounds on its unknotting number? I mean, it bounds a genus 1 ciphered surface, or it has a genus 1 ciphered surface. So the signatures are all going to be, plus or minus 2. But maybe there are some more sophisticated invariants.
So I don't know about the unknotting number. I will tell you that what you just told me says that their untwisting number is at most 2. So your untwisting number is not going to give you a lower bound on your unknotting there.
Okay.
And again, abstracting untwisting number 1 is hard. So,
Sure.
But yeah, the untwisting number is bounded above by twice the cipher, the 3 genus.
Oh, that's not algebraic. That's true geometrically.
That's just true. So geometrically, let's write this.
Yeah. Okay. I had missed that originally. Thank you.
Sorry, I don't think I wrote it down. This is Livingston. That untwisting is less than twice the genus. So if genus is 1, then your untwisting number is half that 2.
Okay, great. Thank you so much.
So when we do twisting operations, the regions don't have to be distinct regions, right? I could twist and then grab some of the strands from that twist along with some other ones that are different twist, right?
Yeah.
Fine.
Yeah.
So my question is like, is there anything? I mean, this seems sort of a difficult question, maybe, but consider some, link that we're going to twist or not. Is there anything that people study about these things or like get efficient or not?
Okay, so let me see if I can restate this, restate your question for the rest of the audience. So the question, I believe, if I'm wrong, the question is, okay, so you do some twists and then you look at the diagram and you do some other twists, and can you look at all of those like twisting unknots? The unknots are twisting along in a single diagram, and then can you examine the linking of that, or how those links work?
Maybe in addition to the knot.
In addition to the knot?
Yeah.
I'm sure you can. I think that just because we have so few examples where well, I guess if your untwisting number is large and you can actually write it down, then maybe you could. But I think computing these things is usually like find one and then compute the signature. Yeah, I don't know. That's an interesting question. I know people, I think Chuck Livingston in particular, and maybe I'm forgetting, maybe Mohammed, I know, have thought about this. If you take off the null-homologous condition, at the very beginning I said the null-homologous condition, everything either is 1 twist or 2 twists or the unknot. Then with the 2 twisting situation, you can ask this question, and people have actually thought about like, what do those 2 twists look like? But maybe not in the null-homologous case.
Any more questions?
But
Thanks, everyone.
next talk at 11. For those of you on Zoom.